let's get back to that quite exciting topic now that we started yesterday, which is magnetostatics. And there we saw that if you have moving charge, actually, you also have a magnetic effect. That was first observed by Oersted then when he had a compass needle close to a um, um, wire carrying current, and they noticed that the compass needle is actually being deterred. And so there's the observation that there is an interaction between magnetic and electric effects. And what we saw is that there is this, I mean, that was how you can describe it, is that you have a Lorentz force that describes the force which is acting if you have a moving charge to a magnetic field. And the important thing is you have to remember really this relation here and this right-hand rule, the thumb right-hand rule, because if you are taking uh, the first thing here, that's the velocity that is signified by your right-hand thumb. You look in what direction that goes. You have here this picture. The thumb goes up here along aligned with the blue line. Then the second quantity, that's the B field. So because the right-hand right rule, that means you now take your index finger and direct it in this direction where the B field is oriented to. You see, so you see that you have a motion of, you have the motion of that particle in V direction, and then it is the force is perpendicular to both the direction of the B field and the direction of the um, of the um, of the moving particle. Yeah. So if you take that, you have here the velocity um, vector is blue. You have here the B field coming out of the plane. So then you see where your middle finger is directed to, that points in the force direction. Yeah. So you're familiar with this uh, uh, right hand three finger rule. So you see here, this is you have here the cross product, and this is general formulation. You have A cross B, that is shown by the index finger. A is the thumb, B is the index finger. And so the interesting part is, if you look at also another interesting aspect, if you look at the work or energy that is being added or taken out of the system, you would think if you integrate over force over a line element, you see, because velocity, the velocity vector is basically, we are following here on a trajectory, dr, or we're moving it along some path. We decide on this dr, but that basically determines here also, that is in agreement with this direction, which is given by the velocity vector, obviously. So the velocity is the dr by dt. And you see that this component here, whatever comes out in this cross product, is perpendicular, because the dr is already here in this cross product. If you take here, then this with the inner product of the line segment, then you know that this force here, this gives you the force, and this is the integration path on the force. You see that these two are perpendicular on each other, and that means there is no energy or also no power being added in course of this Lorentz force when you have a magnetic, an electric particle moving through some magnetic field. So then we were more qualitatively arguing what is happening, because all details you get in the printed notes, but we were arguing what is the trajectory, what motion will we obtain when we have such a particle, a charged particle entering a magnetic field. Then we have to take into account Newton's law. We have here the equation of motion. The force is given as a mass times the acceleration, which is a time derivative of the velocity. And on the other hand, in this equation of motion, the force that is acting on the particle, that is changing possibly its direction, or at least it can also change its the energy that it will absorb or will get as kinetic energy. I mean, not absorb, but which will add it to it. That is the Lorentz force. And the Lorentz force is this Q times the cross product of velocity and B field. And then we have written out this cross product. We have assumed that in this simplified example, we have a velocity component in any of these directions, but so X, Y, and Z, but the B field is purely oriented in Z direction. And as a consequence, there was no contribution to the Lorentz force in Z direction. So we wrote this equation of motion by these different components, the one for the X, Y, and Z, and we have basically three first order differential equations which we have to solve, and the first two are coupled to each other. The third one, however, in this case, is very thankful to us. It is very good to us because that we can solve isolatedly. And here we see just that because the time derivative is zero, that also means that the velocity in Z direction remains constant from whatever the initial velocity in Z direction is, it remains constant. On the other hand, so we divide our velocity vector into two components, one which is parallel aligned, which we call V parallel, and one which is perpendicular aligned to the orientation of the B field. And these velocity component, which is perpendicular, so which is basically describes the motion of the particle in a plane here, perpendicular to the B field. This is this vector here. And here we also concluded that because no energy is added, the total velocity has to remain constant. So the Z direction is anyway not affected, but also the velocity component in X and Y has to remain overall constant. And that means somehow, if it is changing, it has to change along a circle. And it is actually changing on a circle, and that gives you this gyrational motion that the particle starts to move in circles. But if it, in addition, has a Z component, it spirals into, it moves also in the Z direction, and you have this helical kind of motion. And that is, can happen now. This simplified version was to get the solution in Cartesian coordinates and have it the B field all aligned with Z, but of course you can have that arbitrarily aligned. So this is what we discussed yesterday. And now I would like to also talk about what happens when you have actually a current distribution. So also then you have the Lorentz force acting on the charges, of course. So we have a current density that we denote with J, small j, times the charge of an individual carrier, the particle density, times the velocity vector. In general, you may have different carrier types. And in that case, you would obtain your current density by adding up these different types of carriers, which I denote here with the index alpha, and then run from 1 to n. So you have, for each of these carrier types, you can define the respective charge that each individual carrier has. Then the particle density, and you can get this velocity. This is basically for us usually the mean velocity according to the drift model. This is for several charge carriers, for several types, let's say, or species of charge carriers. So now we assume that we have one species of charge carriers, one type of charge carrier. So we take this formula in the following. So then we have these, remember we have these n particles inside a volume V. So our carrier density is this total number over the volume. And let's see here, this is n, is a number of particles. So we know that the Lorentz force on a single charge carrier, what that is Fl, the force on one charge carrier, the Lorentz force, that is given by the by the charge value, by the velocity of the carrier, and its cross product, the velocity with the magnetic flux. Now, what happens for n particles? If you have now a great number of particles, then obviously that force will scale up. So you have your force is an n times q times cross product of velocity and magnetic induction. Now, and the flux density here. Yeah. So let's divide that total equation here by the volume, right and left hand side. Then you get a force per volume, and on the other side you get this number of particles per volume times charge times velocity and the cross product with the magnetic flux. And the absolute number of particles divided by the volume, that is of course the particle density times Q times V cross B. And there you recognize that this here actually is something familiar. This is our current density, this term. So you can conclude that we can write the force per volume as the current density and its cross product with the magnetic flux. And this quantity, force per volume, that we can introduce here for this, the force density. This becomes then a small f, and it's also a vectorial quantity. So this is basically this one here. And this is force density, which is a force per volume. This is known also in the printed note as equation 3.9. That's Lorentz force density. This is acting on a current density. So why are we doing that? Because now we want to see actually what happens if we don't have individual charges, but we want to work with whole lot of moving charges. So that basically is expressed by currents and by in a local form by the current density. Oops, where did I go? So yeah. So now, since you have the force density, you will obtain the total force by integrating the force density over the volume of a conductor. If you want to know the total force on the current, you integrate over the volume of the conductor and basically over the force density. I can give you I forget, I give you that sign up. So we're integrating over the force density over the volume of a conductor. Then we get the complete Lorentz force that is acting on a given current. Remember, the total current is obtained by taking the current density over the area of interest. And if the force density is constant, then that means if it is not a function of the position, then you just have to multiply by the volume. So let's look how that turns out then when we really want to see what the Lorentz force on a conductor is. So we want to know the Lorentz force on the conductor. So we already indicated we want to work with the force density, which is given by current density cross product magnetic flux. So this is our force density. And the unit is then, or it's not the unit we already, this is of course Newton per volume, but this is basically to what you have to think of, that this is a force per volume. This is a Lorentz force per volume, so to say. So it's a slightly new concept maybe. Force per volume. So we have the force, that the Lorentz force on the conductor. So we have want to know the total force on a conductor, which carries charge and moving charge. So this is obtained by integration over the volume of the conductor. Carries a current, right? Carries a current, and we integrate over the entire volume. The current density as a function of position, and everywhere the cross product with the magnetic flux. The volume of the conductor, and this is basically, I'm just writing it here once more, but you see that this, when you integrate over the conductor, that means you integrate over the volume, and instead of the differential V, what you also find as a way to write it is that you here have to the power of 3 here the differential length element. That is an alternative notation here, and this is your force density. I think this is an equation 3.11. Yes. So now let's simplify this to a cylindrical wire, and that wire you see here, we do it now the simplification, and you see in the wire you have the current coming in. You have here, you can give the current also here as a current density. So the total current you obtain by integrating the current density of any of these cross-sectional surfaces. And you have here a line element, the delta S here, the ds that follows your wire. And we make now a few assumptions. One assumption is that the cross-section of the wire, this A here, that should be constant over the entire wire. So we have as you keep having a constant cross-section. Then also the conductivity of your wire is homogeneous, so it doesn't change anywhere in the wire. And the current also, the current density, that is always given as a tangent to the wire. So the tangent is here, and the current is not flowing in any other direction but into the tangent of that wire. And that means you can say that the current density, the absolute value, is just given as the total current through the wire divided through the cross section, and that is constant. Also, we said this is true for the magnitude, but we said the direction of flow is always given by the tangent to the wire. So it means we can take here the absolute value of the current density times the tangent vector. And the circumstance that the conductivity is homogeneous and is not changing the sigma here, that is also reason for why we have our magnitude of the current density constant, because we would only have a non-constant on our current density would only vary if that was not the case, if the conductivity would also vary. So basically our current is in its orientation also parallel to the E field. So now we want to integrate over the via, so you can do the parametrization of the curve. So we make a curve that can be where the curve vector r that can be given as a function of this parameter s, and the tangential component is here this parameterized r derived with respect to s. So you have so the force on the via obtained by taking the volume integral over the cross product of current density and magnetic flux over the volume. In this volume integral, you can split up in that curve integral that follows the via and the cross-sectional integral. Then we have set we insert now the points that we have concluded for our current density, so that we have an absolute value which is constant over the cross-section, and the direction is following the tangential vector of the curve describing the curvature of how the wire evolves or wire bends, and then the cross product with the magnetic flux here. And we integrate over the surface and over the length. You see the volume element, the delta, the differential volume element has been split up in a differential area and a differential line segment element. So this is our curve integral. Then we have our area integral over the cross section. Then we have said that the absolute value of J is given with I over the cross section because it is constant. And now you see, if you evaluate that integral here for the area, so the area enters here, and of course this is a differential element, but if you assess this, you get just the current. I mean, you know, this here basically is the current density. And on the other hand, you have the integration here, tangential component, and the differential line element, but that is basically the line element in vectorial form. And so you obtain an integral over that path that describes the wire over the current, and the orientation of the current at each differential element with the cross product of the magnetic field. So basically you have now you're using under these assumptions we had for the Lorentz force earlier, the velocity and the cross product of the velocity with the magnetic flux, and now you're taking the orientation of the segment of the wire, the differential segments, with the cross product of the magnetic flux, because you know that under these assumptions, all the charge carriers flow in alignment with that differential element of that wire. So the force on the wire is given the curve integral here. The I is constant, and you can write it here as the cross product of the magnetic flux. And then we switch the order here, because we have combined here earlier here in this step here, you know, we have taken the tangential vector, which we actually introduced here for the current density, but we pulled it together with this differential line element, and we formed the vectorial differential line element here. And we have put that in here, but now let's flip the order. so that we have our vectorial differential line element here at the end of the integral. But in order to do that, we also have to consider that we have to switch here the sign, and then we can write it like that. We have, if you flip the order of the two vectors in the cross product, then you have to account for it with a minus. That immediately you can see from the right-hand rule. And this here is then our equation 3.12, and that's the Lorentz force on a current carrying wire. Thank you. Everybody has signed? Here? Yeah? Okay. And C is a curve with a length L of the wire. And if you look at the force on just a small part of the wire, then you would get the D of the force on the wire by taking just the minus A times magnetic flux across the orientation of that wire segment. This is equation 3.14. So that, I think, is also quite intuitive, because you have, we first saw that you have a Lorentz force that is acting on a moving charge in a B field. And if you have a wire, then you have to take all the charges which are in there into account. And you see, if you have this wire that has the ideal condition that it is uniform in its cross section, I mean, it has constant cross section, it has no variation in its conductivity, then you can say that by integrating here, you can obtain this formula. You have the total current and the line orientation of that particular line segment, and all the charges are flowing in this line segment uniformly and in alignment with the line segment itself. Then this is what you obtain. Now, what you can think of as an example, if you have a wiring carrying a current I, now you can think of having here this wire attached here to some solid, maybe hanging from the ceiling or so, and you have here this wire here, this small piece of wire, and it is connected here so that you can get some current into it. Then you have a B field which is oriented also here in the vertical direction. Now, what are the contributions to where do you have contributions here to the force? So if you look at the right-hand rule, here where the current comes down, you have the direction is actually where the current flows is in alignment with the B field, so there is no force acting on it. The same here at the end where the current moves up again, there is its orientation, the direction of current flow is in alignment with the B field. So you only have here, you have a current that flows in a direction which is perpendicular to the B field. Now, let's take the right-hand rule. This is a flow of the current. This is a direction of the B field. So then this would be your force vector coming out here. So this is the current flow. So you have a force that is acting then in this direction. This would be your small wire element, and this small segment here of that wire. So the current flows in this direction. This is the direction of your current flow. So then the wire here will experience a force which is not vanishing. So I have said this wire is this wire segment. This is here. You have this current coming from above, and you can think of having here some very thin wire, so that this wire element here is basically it is swinging, like you can use it like a swing. So you have a wire swing, and no Lorentz force is now acting on these vertical lines because you have this circumstance that the B field is parallel in direction of the current. But in this middle segment here, there you have some force. And if this is a wire swing, then basically this can be pulled out of this original position now. And yeah, so there's no Lorentz force on the vertical lines. Why? Since the magnetic flux here is parallel in the direction of the current in these vertical lines. And this is given by the current direction is always given by that orientation of the with the line segment. And there you have the Lorentz force on that segment, or you write it. If you reorder it, you have to account for the minus sign. So now assume that the B field is constant, then you have that. So if this happens now, if you have constant B field, if your current here flows fully perpendicular to the B field, and this will be the situation in the wire swing, because also if you pull it a bit, then according to the force of the force to the Lorentz force, if you pull that swing out of its balance position, this segment will keep having a current which is running perpendicular to the B field. So the total force on the wire you obtain by integrating here the product of current times the magnitude of the B field, because we assume it is constant, over the length of the wire. And this is your total force on that wire here. And you have, of course, a lot of useful applications that would be, for example, here, when you have an electromotor. That is an example where your Lorentz force comes into action. You have here a permanent magnet, and you have here current flowing through this loop. And this magnet field from outside will cause that Lorentz force on that wire, so that will make this wire loop here to rotate, because it will try to it will follow that Lorentz force. And then here you have some commuting contacts that will then also alter the current flow, so that you can have a continuous rotational motion of that electromotor. Questions? And by the way, I uploaded another exam problem, and I'm planning to do some of those in the upcoming tutorial to solve some of these problems in problem sheet. This is the one that I uploaded today. In the upcoming tutorials next week. And so that's probably a good idea. You could already look at those and try to solve those, because it typical exam problems, and then we can see that we solve some of them in the tutorial upcoming. Because for the other ones, there are anyway also solutions posted, but these maybe that's something good one could do then together in the tutorial. So we're getting to chapter 3.4, 3.3 that I'm not going here further in detail. You will see that in the lecture notes, but this is about permanent magnets. This is not so relevant now for us. I want to talk about some differences between the magnetic field and the electric field. And what you see here, that you have seen quite a bit of times already, this is on the left-hand side. This is the E field, which is generated by charges. We had the situation where we have a single charge here. This is a plus charge. So all the field lines go out in radial direction, right? This is what you call a monopole field. Now, we had also a situation where you have a plus and a negative charge. And you have the field lines going here from plus to minus. And this is a dipole field, because you have two poles, so it's a dipole field. And how does it look? This is for the electric field. This is what we covered in electrostatic. Now we are at magnetostatic. And the field looks a bit different here. We'll see that we will get to how this field is looking, and that you actually hear the first example. It happens actually when you have a current carrying wire, then this is generating a magnetic field, which is oriented here in this circular fashion around the wire. So you have current flowing out here, and you have a magnet field that is forming due to that. Now, how does it look for such a magnet? If you have a permanent magnet, for example, then your field lines, they run here from north to south. And actually, they're not stopping at the north or south pole. They're running here through this magnet. That is a very important thing. And they're running from north to south. And the inside, they keep also running. So this is quite a difference. The special aspect is with a magnetic field, you cannot have a monopole field. You can only have dipole fields. You see, electrostatic field, you can have a single charge and force lines run out in radial direction from that charge. But for this magnet here, your field lines here, they are always closed. They always form a closed loop. You see, these here do not form loops. So what is the source of these fields? If you look at the electrostatic case, you have the fields are basically generated by these individual charges. And for that, what is very important is to consider the Gauss law. So the generation of electrostatic field, that is described by Gauss's law. And I write that down for you, the Gauss law, and then we see it again. The generation, so let me also add in this remark that I just given. Here you see you have always closed field lines, And here in the center of this current carrying wire, and this also explains, if you think here at this Ørsted's experiment, he brought that compass needle close to that current carrying wire, and this magnetic field that you see here that is generated due to this current flow, that caused the deviation of the magnet needle. So getting back here to the electrostatic field, you have the generation of the electrostatic field that is described by Gauss's law. Do you remember? That is the integral over a enclosing surface over the D field, taking here the vectorial surface element, equivalent to all the charge enclosed in that volume, or that we had also given as volume integral over the spatial current density, spatial charge density. That is Gauss's law, and we also have given it in differential form. Yeah, what is wrong? Why does it keep in differential form? We had it as a divergence of the D field is given the space charge density at that particular position. Or you can also write that as divergence of epsilon times E. And actually, this is the first Maxwell equation. We come later on at the end of the lecture, we want to have Maxwell's equation, which described the electromagnetic interaction, the interaction where an electric field causes a magnetic field, and that again an electric field, and they are mutually to this interaction, you have the phenomena of an electromagnetic wave which can propagate. And these Maxwell's equation, they are one of those you have here now. The others we are getting to as well. This is the first of Maxwell's equations, maybe. That would be a better way to write it, but put it that way now. And you have these sources of, you see how it is related to the source you have here the D field, that is, as you see, the permittivity times the E field, and it is related to the charge. So these charges are causing the E field, so they are the sources to the E field. And so we can say sources of the E, or also respectively of the D field, are electric charges or also charge densities. And for the electrostatic field, at these sources, the field lines end or start there. So end or start at sources. So if you look, however, to the magnetic field, here you have visualization of the E field by small iron particles, as in the video here, by the way. So for the magnetic field lines, the thing is different. We don't have them ending or starting somewhere, but they are always closed. As a consequence, or the reason why they have no starting or ending is because there are no magnetic monopoles existing. These are simply not, this is not existent. You have no concept of, for example, of a magnetic charge that does not exist. So no magnetic monopoles exist and no magnetic charges exist. And what does it mean? There are no sources, and hence this B field, the magnetic B field, is source-free. And so it's a source-free field. And it is also called, then it's a solenoidal field. The field is solenoidal. And what does it imply? That because we had in the electrostatic, we had Gauss's law, and we said that if you take the divergence of the flux density, it gives you the local sources. Now we have here in the magnetostatic scenario the flux density B, the magnetic flux. And if you take here the divergence of B, then that is 0. This is equation 320. Or if you write it in integral form, you get the closed surface integral over the control volume, and you integrate the magnetic flux, the B field, and it will become 0. That is the equation 319. And these are basically the second of Maxwell's equations, which states that the flux of the B field through a surface, so closed surface of a control volume is always vanishing. So this, if you look what that, if you compare that to the visualizations that we used for Gauss's law, what does that mean? You have here a scenario where you have a B field, and we say that is always closed. Nah. Okay, it should be okay. That's reasonably well. So you have these field lines, and they are always closed with an orientation here. And if you are taking here your control volume, like we do also for Gauss's law, but now you see that the divergence of the B field here, this time this is a B field, then everything that enters as a flux into this control volume is also leaving again. And this, that the divergence of the field is vanishing, that is basically the mathematical formulation for a source-free field. This here is the mathematical formulation, the circumstance that it is a solenoidal field, that the divergence of that field is vanishing everywhere, is the formulation for being a source-free field. In contrast, you had the scenario in the electrostatic case. You had field lines which start or end in this volume. They start or end there at the source. Yeah. So, for example, you have your charge Q, and then if you take your control volume here, you will have field lines in this case which are starting, and if it had been a negative charge, they would be ending there. So you have the integral over the closed surface here is not vanishing if there's a charge included. So as a consequence, you have seen that we used Gauss's law to derive the B field in electrostatics, but this doesn't work now because if we use the divergence or we use the surface integral over the magnetic flux, then we cannot use it. So we can not, based on these equations here, like we did on the Gauss law, we could use that. We had a charge distribution somewhere given, and we could use this to determine the electric field. But here, this will not give us anything because this is just zero. So the 319 and 320 cannot be used to calculate wave fields because, yeah, I mean, not because, but they cannot use them. But however, nevertheless, they tell us something about the nature of the B field, though. And what is this? Something about the nature of the B field. And so what we have already a bit hinted to is, but what can be observed in experiments is that the B field, if you have a current that is flowing somewhere, you get this circular B field around it. So this is something that is found by observations and experiments, that if you have a current that is flowing here in this wire, then in consequence to this current, you will obtain a B field which is circularly oriented around this wire. So you have a circular B field, and you have here the circumstance that currents I, or current densities also, of course, they generate B field. And that will, in the end, bring us to Ampere's law. And that will enable us to calculate magnetic field. But that is coming up soon, just where this is heading to. This is heading to Ampere's law. That will be part of Maxwell's equation also, which will enable us to calculate magnetic fields. So now you wonder why I say this is source free, and at the same time I say it is generating this B field via if there's current flowing. Let me give you a comment on that too. From I or J, we can calculate magnetic fields generated from I or J. That will go here to chapter 3.5. So if this current here gives you a magnetic field, then it is generating it, but it is not a source in the mathematical sense, because in the mathematical sense, for being a source to the field has to, your field lines basically have to end or originate out of this source. So this is not the circumstance that you have here. You have a magnetic field, and it is generated through the flow of charges in that wire. So it is generated through that current. But the field here, that if you look at the generated field, in the mathematical sense, it does not have sources because the divergence is vanishing. It has, however, a different property that we will see later. But for in the mathematical sense, that means their field lines are not ending anywhere. They're always closed, so they have no source to spring from, or where they end, no sink. So in the mathematical sense, that means the magnetic field is a source-free field, because the divergence of this field is always zero. So of course, you can have here a current and it generates a field, but this field is source-free. So this is a mathematical concept of the field, because divergence is vanishing. And that such a field, which is always source free. I mean, you have regions of the field in the where you have no sources in